So, dear colleagues, after 1 month without meeting, today's day to continue our Kharkiv chemical seminar. And our speaker today is Professor Dr. Manuel van Gemmeren. He obtained his chemistry diploma from Albert Ludwig University in Freiburg in 2010 and a PhD from Max Planck Institute for Köln-Forschung in 2014 under the supervision of Nobel Prize winner Benjamin List. He then conducted postdoctoral studies at the Institute Catalia Investigatio Chimica from 2015 to 2016, focusing on the reductive carboxylation of inert CO bonds. In 2016, he began leading an independent research group at the University of Münster. From 2017 to 2020, he served as an Otto Hahn research group leader at Max Planck Institute for Chemical Energy Conversion. From 2020 to 2022, he led to Emmy Noether research group at the University of Münster. In 2022, he became W2 professor and director of organic chemistry at Kiel University, where he also assumed the role of active managing director of the Otto Diels Institute for Organic Chemistry. His research interests lie in the development of catalytic controlled selective transformations and ligand design. He also investigates aliphatic CH activation, indirect activation of CH bonds in aromatic compounds, and chemical mechanisms, along with optimizing screening methodologies. Professor van Gemmeren has received multiple scholarships and awards, including ERC Starting Grant, the Docent Prize from Von der Chemische Industrie, the Otto Hahn Award and Medal from Max Planck Society, and membership in Alexander von Humboldt Foundation. In addition to his academic and research accomplishments, he serves as an associate editor for SynLab and has provided extensive peer review for leading journals, including Science, Nature, Angewandte Chemie, and other. And dear Professor van Gemmeren, so you can start your lecture.
Thank you very much for this kind introduction, and I'm very happy to share the recent results from my lab with you today. As a general to give you a general feeling for what motivates my lab and my team members, we basically start out with the question of what is the role that synthetic organic chemistry has when we interact with other disciplines, when we speak with physicists, with biologists, with people from medicine or pharmacy. And in the end, the most important thing we do is that we are able to synthesize molecules. And these molecules are then relevant in so many other fields. And this is something that we have to be aware of, that it can become a problem. For example, in this quote, which is roughly 20 years old, but is still very much current, the bottleneck for biological research was found to be the availability of the molecules that we're supposed to make. So we still need to develop even more methods and more flexible methods so that we can provide the molecules that other people need. And specifically, what we need synthetic methods that allow us to make the molecules that are currently difficult or even impossible to make easily, because only when they're easy to make, they are within the chemical space that other disciplines can really use. They have to be able to count on easily being able to make molecules. And if we want to do this, we need methods that allow us to very rapidly build up molecular complexity. And those are the methods that my lab looks for. Because of this, we have to think about what is complexity, because only when we understand how complexity comes into molecules, we can then selectively introduce it. And complexity actually has very different meanings depending on the area of science that you're in. So the question is, for an organic chemist, what is complexity? And we can intuitively say, okay, ibuprofen is a comparably simple molecule. And without needing any specific rules or guidelines, we can say palytoxin is much more complex. And E.J. Corey has already done a very nice job for us to distill out the things that make a molecule complex. And amongst the most important ones, it's the size. The bigger a molecule is, the more difficult it will turn out to make. It's the topology, specifically ring closures, ring junctions, that can make a molecule much more difficult to synthesize. of course, the presence and the configuration of stereocenters, and the presence and the nature of functional groups in the molecule. And these are the things that we need to be able to control so that we are really building up suitable molecular complexity. Now, what my lab does is, because of these thoughts, always centered on method development, and we do different things that all touch on this central motive. And one small thing that I want to mention, because it's also important, is that in my lab, everybody needs to be active and skilled in traditional organic synthesis. And what I mean with traditional is that we need to be able to also apply and use synthetic methods that are not the ones we ourselves develop. And we use these both to make ligands or as part of collaborations or to synthesize the substrates we need for testing. And every once in a while, we actually realize that there is a method that we would like to use, and this method doesn't exist. So there's a few cases where my lab has actually developed organic methods that have nothing to do with our main area of CH activation. For example, we have developed a protocol. This is shown here stepwise, but it's a one-pot protocol where you can convert an alpha hydroxy ketone directly into an alkyne. And this is quite useful if you think about how the hydroxy ketone is made. This can be made by an acetylene condensation, and then in 2 steps, you're making a completely new alkyne from 2 separate fragments. Similarly, we found that there was no selective method to synthesize a mixed dithioacetal. And we actually developed one that under kinetic control gives you selectively the mixed compound rather than the 2 homodithioacetals. And this was then one step on a longer project. And this longer project enabled us to ultimately develop a new olefination reaction. So similar to, let's say, a Wittig reaction and so on, where you need phosphines, we here use a thiol and an aldehyde, and we convert them in a stepwise, but in principle, one protocol into a new olefinic moiety. This is just to show to you that besides all the CH activation chemistry that I showed to you today, we are also very much by heart synthetic organic chemists. But the focus of my talk is, of course, today as well on CH activation. And within this area, I want to give you a second introduction, so to speak, to explain to you why we think that it's worthwhile to study this field. And in the end, it boils down to what I just mentioned about complexity. If you think about it, just look at these 2 molecules. It's essentially the same molecule, just drawn in 2 different ways that we have. It's both times ibuprofen. And now ask yourself, why is it allowed to use the left structure? The right structure contains all the information as one would learn in a basic organic chemistry at high school, for example. Nevertheless, we're very much used to the left structure. And this is because the left structure allows us to see the important things directly. And this, by implication, means the CH bonds are very often not important. And they're not important because they do 2 things. They limit the size of the molecule, and they at the same time are very often unreactive. So arguably, the CH bond is the least complex thing that you can have. And if you can take this uncomplex thing and directly convert it to what you want to have in your molecule, that is, by definition, the fastest way to go from simple to complex. And this is why CH functionalization reactions are so attractive. And even more so, if you think about an ideal synthetic toolbox where you have not one method for CH functionalization, but several, and each of them allows you to go to a different position in a complex organic molecule, because then you can really mix and match and build up directly what you want to have without detours that you need in order to induce selectivity. But of course, it's in real life not as simple as that. The key message that I want to give to you is that we need different tools to functionalize carbon-hydrogen bonds. And if you think about it, carbon-hydrogen bond functionalization has been done for a very long time, but through routes like this. The first functionalization step is often a reaction that we learn in basic organic chemistry, like an electrophilic aromatic substitution or a radical halogenation of an alkane. And then when you first have a functional group in your molecule, you can continue, you can convert it into an organometallic, think Grignard reaction, for example, and you can then cross-couple or further functionalize your molecule to reach the target structure. This is also a functionalization of a carbon-hydrogen bond. But if you want to get more specific in the terminology, a carbon-hydrogen bond activation, that's what we research, is a step that takes you directly from a carbon-hydrogen bond immediately to an organometallic intermediate. So a functionalization of carbon-hydrogen bonds that uses CH activation can be shorter and milder than other processes for CH functionalization because we don't need the first step, the harsh pre-functionalization. And from our perspective of molecular complexity, the most important feature is that CH activation can in principle aim at a different carbon-hydrogen bond in a complex organic molecule than the one a traditional activation process would target. So we have the chance to really build a complementary toolbox by using this tool of CH activation. Of course, all this potential comes with a price tag, and the price is we have to find catalysts and conditions that allow us to overcome the extremely high stability of carbon-hydrogen bonds. And once we have a catalyst and conditions that cleaves carbon-hydrogen bonds, we have a second problem. Even our prototypical simple organic molecule ibuprofen already has a lot of different carbon-hydrogen bonds. And if I cannot choose which one I activate, I will make a horrible mess and it will not be useful synthetic chemistry. This is why a lot of methods in CH activation rely on the use of so-called directing groups. And a directing group is just any Lewis basic site that can coordinate the metal. And by coordinating it, it brings the metal close to the carbon-hydrogen bonds. You have an intra instead of intermolecular reaction. This gives you reactivity. And now the position of the directing group in the molecule tells the catalyst which CH bond to functionalize. So we also solve the issue of selectivity. But of course, these directing groups, I need to introduce them and I need to remove them afterwards. So this advantage of directing groups doesn't come for free. And this is the point where the logic of my group kicks in. We want to design catalysts that can overcome these limitations. For this, we need to think about mechanism. This here, what I'm giving you is the most simple sketch that you can boil down a typical CH activation. And what happens here is very often with palladium, at least, that the CH bond is cleaved with the help of a ligand on palladium. And the ligand acts as a base and takes up the proton that is being formed during CH activation. And at the same time, the metal acts and takes up the forming C-. And what we can now do to understand the mechanism of such processes is to monitor the two key bond lengths. We can monitor the bond length of the newly forming carbon-metal bond and of the old carbon-hydrogen bond. And if you think about what has to happen, the carbon-hydrogen bond has to go from being there to not being there. So the bond order has to go down to 0. And the carbon-metal bond has to go from non-existent to existent. So it has to go from 0 to 1. And that means that the CH activation process takes us from the top left corner of this square that I'm showing here to the bottom right corner of the square. And this scheme that I'm showing to you, it's called more a Farrell-Yanks diagram. It can also be used, for example, for elimination reactions. And it helps to distinguish between different mechanistic scenarios. For example, in this drawing that I've given you, going via the corners would be a stepwise reaction. And going through the middle of the square is a concerted mechanism. If I'm going exactly through the diagonal line, it is a concerted and synchronous mechanism. And if I go to one of the two halves of the square, I have either electrophilic or an electron-rich system. And these two are now very decisive if I want to develop selective methods. And the reason for this is that in one case, the one that I've labeled as electrophilic catalysts, the CM bond formation is the more strongly driving element. And this means that the electrophilic metal wants to be attacked by electron-rich positions. So mechanisms that go through this area prefer electron-rich positions of the substrate. On the other hand, where I wrote electron-rich catalysts, in these cases, it is more the deprotonation of the carbon-hydrogen bond that's driving. And this means that because I accumulate negative charge on the carbon, the driving force is to activate the most acidic carbon-hydrogen bond. So depending on where I am on this scheme, I will be able to induce different selectivities. And besides these selectivities, I need to be able to control this, or I have to, in order to later on control this, I have to be able to choose ligands that help me navigate where on the square I am. And to understand the literature in this field, I'm showing you here 4 terms that show up a lot. The first ones to study these mechanisms were, on the one hand, Gorelsky and Fanu, who called this concerted metallation and deprotonation. They were working with electron-rich phosphine catalysts and heteroarenes or electron-rich arenes, and found a preference for acidic CH bonds. In parallel, McGregor and Davis studied more or less the same thing, but in directed CH activation, so with directing groups on the substrate, and they called this AMLA, amphiphilic metal ligand activation. These systems all tend to prefer the acidic positions. Later on, people discovered that there's also similar concerted mechanisms, but with the metallation as the driving force. And the first ones to describe this was Ackermann, who called it base-assisted internal electrophilic substitution, or BS. And sometime later, Caro rediscovered the same phenomenon with a different metal and called it electrophilic CMD, inspired by Faneu's terminology. So whenever you meet these terms in the literature, you can now associate this with a specific type of reactivity and also with an expected regioselectivity. And we're going to need this throughout this presentation. Last but not least, how can we tune our catalysts? Well, we need to think about what kind of ligands we can apply and what they do with the catalyst. On the one hand, the first systems that were described were basically palladium acetate and a substrate with a directing group. In this case, the only thing I can do much is I can choose different carboxylic acids. And this has already been used quite successfully. Sometimes a method got way better when going from carboxylate to pivalate or to mesylate. So this is an absolutely valid strategy in ligand design. Later on, people discovered that adding pyridines on top improved the systems dramatically. And most importantly, it gives us a lot of flexibility. Now we can tune two ligands in order to achieve the desired reaction. And another very important discovery for this talk was Engle and Yu, who described that amino acid-derived ligands, like N-acetylglycine, for example, can greatly help these types of reactions because now we have one ligand again, but one with three separate design elements, the backbone, one anionic donor, and one group that serves as the internal base, or CMD base, people call this sometimes. So now I have a real library of possible ligands that I can study to develop new CH activations. And with these tools that I've introduced to, we will now look at two areas, aliphatic CH activation and aromatic CH activation. In the first area, we basically started our studies with this finding here. When we started in 2016, there was no generally useful method to take an aliphatic carboxylic acid, activate it in the beta position, and introduce functional groups there. There was some isolated and highly specialized examples, but the majority of tools was like this. People introduced a more strongly coordinating group, then functionalized, and then cleaved off the so-called exogenous directing group again. And we argued we want to find catalysts and conditions that obviate this detour. And the first work that my group actually published was a direct arylation of carboxylic acids that now really works with propionic acids. So it doesn't matter if you have a quaternary center in the alpha position, if you have a branching point, or if you have unbranched propionic acid, you can arylate all of these with equal efficiency, simply using N-acetyl beta-alanine as a ligand and a suitable silver salt and base. We could also show shortly thereafter that we can use a similar approach to form carbon-oxygen bonds. This was the first report for a C-heteroatom bond formation directed by a free carboxylic acid. It was enabled by design of sodium isofluoropropanolate as a traceless base in the system. And we could show that we can induce similar alkynylations, again, by introducing a new ligand that was known in other research areas but had not been used in CH activation. With these findings, we then continued and asked, what are the next steps of using similar systems? And first of all, you have to show that you can apply them for something. So we introduced, or we demonstrated a short synthesis of a bioactive compound. And a quick note, we could show that stereocenters that are already present in the substrate do not epimerize. So you don't generate a stereocenter in this step, but if it's already there, you keep the stereocenter, which is also useful for planning organic synthesis. We then realized that everything we'd been doing was functionalizing the beta CH bond. And this is logical because the beta CH bond forms through a 5-membered transition state and a 5-membered Palada cycle. And this means that we are kinetically very much favored. While if we want to go to a 6-membered system, like I'm showing it to you here, we now need to go through a 6-membered transition state. We need to go to a 6-membered Palada cycle. And this implicates that we are kinetically and thermodynamically disadvantaged compared to the 5-membered systems. So we asked, can we, in principle, also induce these gamma CH activations? And to do so, we studied this model reaction here. It's an olefination where you CH activate, you olefinate the gamma CH bond, and then the second reaction error here is spontaneous. You have a nucleophilic site and you have a Michael acceptor, so it cyclizes to delta lactone. And these delta lactones are known bioactive compounds, so we figured this could be an attractive test case. And indeed, we could realize this using just the tricks that we'd learned from the previous projects, combining the right ligands with silver salts and bases. And we arrived at a scope where I'm showing you here a short or a small part of the scope we studied. Very notably, we're directly accessing scaffolds here that are potentially bioactive and are currently being tested for their bioactivity. Besides this, we all had a second big challenge that we identified from our previous beta-CH activations. And this question was, how can we make even more difficult to form bonds? And this here was one of our long-standing dream reactions. We wanted to be able to fluorinate carboxylic acids. And we asked, can we find a suitable ligand and a suitable reagent and a suitable fluorine source to enable this reaction? And in order to figure out how to do this, we actually had to think about the reaction mechanism and what would be key to achieve the desired reaction. Let's look at the expected catalytic cycle here. What we need to have is a palladium source, a palladium-2 salt, that will CH activate the carboxylic acid. This step is known to work on the oxidation state of 2 in palladium. We now somehow have to get to a higher oxidation level. Why? Because it was known that with our ligand systems, a reductive elimination of a carbon-fluorine bond from palladium-2 would be all but impossible. So we need to reach palladium-4 so that this challenging reductive elimination becomes feasible. And we have two chances to do this. We can either have a strongly oxidizing fluorine source that does two things: oxidize and bring fluorine onto the ligand. That's the dashed line in the middle of the catalytic cycle. Or we can combine an oxidant and a fluorine source, one thing that oxidizes palladium and the other one that introduces fluoride into the catalytic system. Now we could quickly eliminate the hypothesis in the middle because all the potentially available fluorinating reagents do not give the desired reactivity, and it's very difficult to design new ones because you have to always keep in mind how difficult it is to make F+ reagents. So we figured it's going to be much easier to design and synthesize different peroxide-based oxidants that oxidation power-wise are all suitable to make palladium-4 and combine them with an F-, introducing this as a nucleophilic species. If then the ligand exchange occurs, we can still get the same targeted reductive elimination in the end. And what this would require would be to find the right oxidant. Because if you look at the intermediates here, the components of the oxidant are present at the catalyst in the key steps of the catalytic cycle. So we can now design a ligand and an oxidant. And interestingly, the systematic design of oxidants had not been used as a concept to introduce challenging reductive eliminations in CH activation. So what we found is the system shown here. We have two very similar ligands that are chosen depending on whether our substrate is quaternary in the alpha position or not. And we have tested different oxidants. And what you can immediately see here is that the ones labeled as oxidant 1 and 2, depending on the substrate class, are the best ones and give synthetically useful yields. And the other oxidants, most importantly, things like tert-butyl hydroperoxide or benzoyl peroxides that are very often employed as oxidants in CH activation, are completely not sufficient in this reaction. So it's not enough to design a ligand. You need ligand design and oxidant design in order to unlock this highly attractive transformation. We could then cover a broad scope. I'm again showing you just a glimpse at the breadth of the scope. The important part here is we can even do substrates where the targeted CH bond competes with benzylic or phenolic positions. So it's even a highly selective process in that regard. And we tolerate a considerable number of functional groups so that we think this is going to be very helpful in generating compound libraries that can be screened for bioactivities. Now, we somewhat unlocked the possibility to combine our CH activations with a palladium-2, palladium-4 cycle. There had been some examples of this in the literature, but none with this oxidant design phenomenon. So we figured maybe we can now unlock more attractive reactions. And one that we were interested in is this one here, to synthesize a lactone immediately from the carboxylic acid. Now, you may have seen this transformation or something that resembles this in literature. So let's look at what was available before we started. On the one hand, it was known that you can use iron, manganese, or copper catalysts and use a hydrogen atom transfer process to oxidize carboxylic acids in the gamma position, and then there's a bounce back, and you close to a lactone. This is useful, and it's potentially complementary to what we want to do, because here the CH activation is selective for highly substituted positions, because the bond dissociation energy of the carbon-hydrogen bonds defines reactivity trends. Besides this, there was also synthesis cases where you can take a carboxylic acid, convert it into a beta-gamma or gamma-delta unsaturated carboxylic acid, and then reach a lactone via an oxometallation or a similar process as a subsequent reaction. The problem with this is that in order to do this, you have very specific requirements to the structure of the substrates involved. A third approach that was known was that that you could do a CH activation followed by reductive elimination if the gamma position was a particularly activated CH bond, except for example, a benzylic or allylic one. But what was missing was the ability to take a simple aliphatic carboxylic acid and then go via CH activation and reductive elimination. And this is complementary to the previously mentioned approaches because the reactivity trend is now primary CH bonds first. So in complex substrates, we will get other regioisomers than with the previously mentioned methods. And very nicely, we could use our experience from ligand design. It will note that the author, Surja, is showing on both of these projects, who also developed the fluorination, could combine our experience from ligand design. And now together with Jiang Shao, this second group member, they could turn this into a selective lactonization that has a very broad scope. And very importantly, this scope also involves beta non-quaternary lactones. And this means we can, for the first time, selectively activate carboxylic acids in the gamma position that do have protons in the beta position. And normally these substrates are prone to lower reactivity and decomposition during the process. So this is actually the first report on a gamma CH activation of carboxylic acids that includes these in their scope. And this is a manuscript that we have currently posted on ChemArchive. And I want to also mention that the ULab just very recently published a related transformation that is already online at JAX. With this, I want to switch the focus to the second major part of the presentation, the aromatic CH activation. And here I want to again enter into the field by showing to you how we ourselves got hooked onto this. If you think about a substituted arene, there's many different ways how you can introduce new substituents into it. Electrophilic aromatic substitution is something we learn typically in the second or third semester when we start learning organic chemistry. And we learn rules. Electron-rich substrates prefer orthopara, halides prefer orthopara, and electron-poor ones prefer meta-substitution. So we can predict this. We can also predict what directing groups in the substrate will do with CH activation. And there's also the traditional orthometallation with butyl lithium and TMEDA, for example. All of this is predictable. And then there are some positions that stay left in the molecule that are not so easy to reach. And we realized that what would be super helpful here would be a non-directed CH activation that is then sensitive, for example, to steric or electronic properties of the substrate, and that would allow us to get complementary regioselectivity profiles to traditional chemistry. Also interesting in that regard is that similar reactions were known with iridium. For example, the iridium catalyzed borylation of arenes, which is sensitive to steric properties of the substrate and is extremely useful in medicinal chemistry. But something like this was not known in palladium catalysis. In fact, before we could even start thinking about selectivity, we had to go to the fundamental challenge of reactivity. When we started this project also in 2016, there was no single method in the literature where a palladium catalyst would take an arene as a limiting reagent and do a non-directed CH activation and functionalization. Every method out there either needed a directing group and was then with the arene as limiting reagent, or the other way around, it needed an excess of the arene. I'm going to show you this on the Fujiwara-Moritani reaction, which is also called oxidative Heck reaction, as a model. What was known is, and this is the finding from 1967, Fujiwara and Moritani, if you boil stilbene and styrene and palladium acetate in benzene, you can make stilbene. But you need the arene that's CH activated needs to be there as the solvent. And then it works with originally stoichiometric palladium a couple of years later in 1969, also catalytic, but never could the authors overcome, or anybody else, the need to put the arene as a solvent. It got better in terms of catalytic activities when people discovered that pyridine ligands can accelerate this. This makes the catalyst much more efficient, it broadens the scope of arenes, but you still can only use arenes where it's okay to use them as the solvent. In contrast, when I have directing groups on my substrate, simple palladium acetate is often enough. Then the directing group tells the substrate which Regis isomer to make, the palladium acetate CH activates accelerated by the directing group, and everything is fine. If this is not enough, for example, because the directing group is only very weakly coordinating, we can also help through ligands and accelerate the effect with directed CH activation. This is the context where I've earlier mentioned that you discovered these N-acetylglycine ligands. Now we can accelerate also weakly directed chemistry. And now we wondered, what if we combine the best of both worlds? Can we design a reaction where the directing group is not connected at all to the substrate? I just have a weak Lewis base plus a bidentate ligand, and now my arene is electronically perfectly activated because the two ligands combined reconstruct the electronic situation of a directed CH activation. And this in fact worked, and I'm showing you here our model reaction after the optimization. An arene as the limiting reaction, an acrylate, an amino acid derived ligand, a pyridine derived ligand, and what we can do is we can functionalize without a directing group, obviously getting mixtures of regioisomers because it's non-directed. But if one ligand is missing or the other ligand is missing, the reaction collapses and we don't get useful yields anymore. So this really only works because of the cooperative action of two ligands. I'm going to show you the mechanism of this later on, but for now I want to stay on the synthetic chemistry part. What we could achieve was first an olefination, which was also shown to be suitable for late-stage functionalization cases. We could expand this to a direct cyanation of arenes, again, without pre-functionalization, you directly arrive at benzonitriles. And we could expand it to a non-directed alkylation of arenes. Now, this is like getting to the products of a Sonogashira reaction without having to halogenate the catalyst, the substrate before. But it's actually not quite. I want to draw your attention to the regioselectivity here. If we have metacresol and we do a traditional synthetic sequence with a silylation, it's protecting the alcohol so it doesn't decompose, we brominate, we do a Sonogashira coupling and we deprotect, we get one regioisomer of the product. And the regioisomer is selected in the bromination step. Due to the big silyl group, it goes para and not ortho. Alternatively, we can use the OH group as an anchor. We introduce an exogenous directing group, and we then do a directed CH alkylation. This sequence gives us, again, perfectly selectively one regioisomer. Now, because of the directing group. And lastly, we can use our method. On the silylated substrate, this gives us a third regioisomer. And this regioisomer is really remarkable. It's formed in the sterically best position, despite the fact that this is not one of the electron-rich positions in the substrate. And notably, steric control of CH activation was well established for rhodium or iridium, but it wasn't a thing in palladium catalysis when we found this. So for us, this was a thing that's unique about these dual ligand catalysts, is that they can be tuned to be sterically controlled. And with this finding, we got really excited about where else we can do steric control. For example, what about heteroarenes? And more specifically, if we look now at a thiophene here. A thiophene with a substituent in the 3 position has an electron-rich C2 position and a sterically more accessible C5 position. And in both directions, there was either no or very little literature. So the C2 selective functionalization was only known for very rare examples, and the C5 was undocumented. So what was our strategy? Well, we know one position is preferred by electron-poor catalysts and the other one by our dual ligand systems. So what if we design one specific catalyst to be electrophilic and another one to be sterically sensitive? Can we then make 2 complementary substrate scopes? Long story short, yes, we can. Here is the electrophilic case. We have a TFA group now on our ligand. It makes the ligand more electron-poor and consequently the catalyst more electron-poor. And this system goes preferentially to the C2 position. If instead we make the catalyst more electron rich and more bulky, keeping the other conditions pretty much constant, we get a different regioisomer using the same starting materials. And I think this is really remarkable that by understanding what controls the regioselectivity of such a process, you can dial in the desired regioselectivity. Another thing that drove our interest was that we finally overcame this reactivity limitation. We can now be arene limited and non-directed. Can we now introduce non-covalent interactions to exert even more control over the regioselectivity? And this question was specifically targeted for charge-charge interactions because of this work that Robert Phipps had published, where in iridium chemistry, charge control could be used to induce regioselectivities. Also, you had shown that a stronger complexation can be used to sometimes control regioselectivities. Based on this interest, we ended up finding a catalyst system that by charge-charge and charge-dipole interactions gives us meta-selectivities that are way higher than steric interactions and electronic preferences could explain. We collaborated with the lab of Filu Maceras at the ICIQ in Tarragona, and they actually found this is the best transition state for the meta-regioisomer, and we looked for stabilizing effects. And if you visualize non-covalent interactions, there's a charge-charge and a charge-dipole interaction exactly as designed, which together explain why this transition state is more stable than the one giving ortho or para products. We can use this to make a scope of compounds, both on the arene side and on the olefin side. But most importantly, I again want to show how this is complementary to other approaches. If I have such a benzyl amine, I can either brominate it, do a Heck reaction, and then after methylation, cross-couple the benzylic position. And this would give me such an biaryl methane, a motif that occurs often in bioactive compounds. I can alternatively go and I can use the dimethylamino group as a directing group, giving me ortho-olefination. And then I do the similar cross-coupling sequence and I get a regioisomer of the same compound. Or I can use our method. I can first form the ammonia, olefinate with our method, and then take the major isomer and cross-couple it. And this gives me, again, a third regioisomer and thereby allows us to more systematically explore chemical space when we build compound libraries. Now, I've shown you what we have done in aliphatic and aromatic CH activation, but I want to mention three shorter parts before the end of this talk. The first one of these, and probably the shortest, is the question of late-stage functionalization. I've shown to you that many of our methods are suitable for complex organic molecules. And now we wondered, instead of reinventing methods for every time we want a new substituent, we have to develop new conditions, can we somehow access a linchpin that, for example, in medicinal chemistry programs will allow researchers to fully exploit the unusual regioselectivities we have? And now what's more versatile than an aryl iodide? So can we make aryl iodides with sterically controlled regioselectivity? And we argued that maybe we can do this using a so-called isodesmic functional group metathesis. So instead of using electrophilic iodination reagents, we would use an aryl iodide to make an aryl iodide. The mechanistic concept looks like this. You start with a catalyst on the top, and then we go counterclockwise. You first do a CH activation, then an aryl iodide comes into play, and we do an oxidative addition. Now we're at the bottom of the mechanistic scheme in a palladium-4 that now has two aryls and an iodine. What if now the other arene does an aryl iodide reductive elimination? Then I would arrive at an aryl iodide, and the arene that used to be the aryl iodide would do a reverse CH activation or proto-demethylation, and it would go to be a simple arene. The only thing we need to do is to tell the two species who is who, in which direction they should go, and we need to prevent an aryl-aryl reductive elimination. And we can do this by choosing the aryl iodide correctly. In this case, if you use orthonitroiodobenzene, both the reductive elimination to make a biaryl is strongly disfavored, and the iodine is very, very unhappy directly ortho to an electron withdrawing group. So once the oxidative addition happens, which is, by the way, also favored because of that substituent, it doesn't want to go back. So the reductive aryl iodine elimination will preferentially happen with what we use as a substrate. And like this, we can now harness the steric control of our CH activation and make a library of aryl iodides that you cannot easily in a single step access using any other method that I'm aware of. Okay, this is what I wanted to show you in terms of utility for building up compound libraries also of late-stage functionalizations. But the next thing that I really want to stress is that we often need mechanistic understanding in order to get to the next step of a catalyst or system development. I've alluded to this before. And I want to show you as an example our mechanistic studies on the dual ligand-enabled arene CH activation. What we studied was the olefination, simply because this is the first reaction that we discovered, and we immediately started studying it. And what we discovered is that there is a really complex equilibrium in which the three catalyst components form various inactive states. These are equilibria with different ligands, with different coordination geometries, and so on. And out of this equilibrium, one active species forms, which is a complex containing one equivalent of each ligand and palladium. We could also show by NMR experiments that it's a mononuclear complex, not a binuclear one. This one now undergoes a rate-limiting CH activation. Rate-limiting also means selectivity determining. So this step decides which regioisomer we get in the overall process. Note the small reversibility arrow. To a small degree, the reaction can go backwards, or it can go back and forth if we don't offer a reaction partner. This will turn out to be important later on. If the reaction partner is present, we go through a series of ligand exchange events and through a Heck-type reaction mechanism that leads to the olefination. After the product is, or alternatively, another series of ligand exchanges can take place. Between these two, there is no conceivable logic. The computational collaboration partners we had just discovered that the same pathway can occur with different ligands remaining on palladium as dummy ligands. For us, this just means that everything converges when the new carbon-carbon bond is formed. This is also clearly irreversible. And then we liberate the product. And a reductive elimination gives us palladium 0. Palladium 0 then ultimately needs to be reoxidized to close the catalytic cycle. Now, what do we learn from this? We learned that the CH activation is selectivity determining. And now we want to come back to the Moore-O'Farrell-Young's diagram that I've showed to you earlier. And we can ask, where is the transition state of our CH activation? Is it more on the electrophilic side, where it should actually go to electron-rich positions? Cannot really be, because that's not what we observed. But we also didn't observe that it prefers acidic CH bonds. We observed that it prefers sterically unhindered positions, so it should actually not follow any of the trends that we've seen before. And now, very, very satisfyingly, our transition state and also the one of directed CH activation in similar systems is extremely close to the diagonal in an area that is normally not populated in palladium catalysis. And this means that our catalyst doesn't really care about acidity of CH bonds or about electron richness in the pi cloud. And because none of these effects is strong, this is why steric influence can play a role, because sterics don't care where on this Moore-O'Farrell-Young's diagram they are. They always have the same force. So the weaker the other effect, the stronger the steric control. And now we can finally explain why we have these unorthodox regioselectivities. But the mechanistic studies that we did also brought us to the last branch that I want to show you here, which is research on isotopic labeling and screening techniques. And it brought us there simply because we observed this reversibility of the CH activation step and asked, can this be used to induce isotopic labeling, more specifically deuteration? And our interest in this is obviously derived from the utility of the potential products. So you can use isotopically labeled compounds to follow metabolism via mass spectrometry. You can use deuteration to fine-tune the properties of pharmaceuticals. You can use it to fine-tune the properties of materials, and we need them all the time for mechanistic studies. So it's extremely attractive to have a good access to isotopically labeled compounds. In fact, this is exactly how one would discover such a CH activation, such a protocol. We realized during our mechanistic studies on carboxylic acids that the mechanism to prove reversibility is you take a deuterated carboxylic acid, you expose it to the reaction conditions, and you check if the deuterium goes away in the remaining starting material. If the deuterium is depleted, it means the CH activation was reversible. But then we should be able to use this step to go from the protic substrate directly to the isotopic labeled one if we apply deuterated solvents. And even more interestingly, we should be able to optimize the loss of deuterium. We take deuterated starting material, and then without wasting deuterated solvents, we optimize the loss of deuterium. And in the very end, when we have the best conditions at hand, we switch to deuterated solvent and protic substrate. We go the other way and we can harness the optimized reaction conditions for isotopic labeling. This is exactly what we did, and it turned out to work well for a broad spectrum of bioactive carboxylic acids, notably not with perfect levels of labeling, but with levels that are high enough to allow us to do metabolic studies, for example, and we're doing this together with collaboration partners just now. What works for the carboxylic acid should also work in the arene world. We should be able to use deuterated solvents and arenes with our catalysts to isotopically label arenes. Now note, we had to develop new ligands in order to get this to a practically useful level, where the CMD basic group, the group that acts as a base in the concerted CH activation, has to be fine-tuned to these trip benzoyl amides instead of acetamides. And for very unreactive substrates, we also need to introduce an N-acetyl sulfonamide ligand rather than a carboxylic acid. But with these newly developed ligands in hand, we can now label both electron-rich arenes and electron-poor arenes with very high levels of deuteration, and notably across a broad range of bioactive moieties. Now, what you may ask at this point is, well, CH activation like this looks nice, but probably you need to be a lab doing CH activation all the time in order to implement something like this. This is probably not like a cross-coupling or a Buchwald-Hartwig reaction that you can do it yourself spontaneously in the lab. And this is something that we heard a lot. So we wondered, maybe we can demonstrate just how possible it is to do this also in a non-specialized lab. And to do so, we actually said we develop a teaching lab course. And this is something that we've just recently published in the Journal of Chemical Education, where we developed a version of our isotopic labeling that now only uses commercially available ligands. It only uses commercially available solvent. It actually, the deuterium source is D2O. It only uses commercially available cheap reaction flasks, as this microwave file that is shown on the picture. And it combines the experience of using our method with very nice NMR spectrometric teaching. Now, besides being able to implement this wherever you are, the other thing that we were interested in or asking is, what about heteroarenes? And this was something that bothered us about the original method. Whatever we did, heteroarenes either decomposed or they didn't label at all. They were just unreactive. And we asked ourselves why. And the logic is, well, heteroarenes, if this is the spectrum of electronic properties of arenes, well, heteroarenes are huge. You have things that are way more electron-rich than the most electron-rich phenol. You have some that are way more electron-poor than nitrobenzene. So how do we even optimize conditions for this? And the truth is, you cannot take one model substrate, optimize the conditions, and then seriously hope that it will work for all heteroarenes. What we instead would need would be several reactions, each of them several optimization campaigns with different heteroarenes, and then hopefully find conditions. But then you don't want to do this in the lab because you're optimizing and optimizing and optimizing, and it's not a really satisfactory way to approach this. So what we said is we will borrow modern screening technology from asymmetric catalysis. We will implement a so-called multi-substrate screening, where instead of having one substrate in the model reaction, we mix various substrates in one flask for each model reaction. We select the substrates such that they don't kill one another, that they don't have undesired reactions, but at the same time, they have to represent the electronic properties that we expect to find in our later scope. We then run the reactions. Each screening reaction has a mixture inside. We optimize the analytics so that we can every time analyze the level of deuteration and the yield of every component in our mixture. We optimize, and after optimizing only once, with the work that we would usually use for one single model substrate, we get several sets of reaction conditions. And these sets of reaction conditions are then validated, and we show that they really work when we have only one substrate around. So this is what we did. I'm first showing you, we found 4 sets of conditions with these 5 model substrates. And I'm showing you here, and it's an interesting extra bonus, you get all the results for all conditions from all substrates during this. But here I'm now showing you the final conditions, which are best. Conditions A have worked for furanes and for thiophenes. Conditions B work for the oxazole. Conditions C work for the pyrrole, and D for the indole moieties. And each of them now works so that we get high levels of isotopic labeling, high yields. And if I go back once, you see that really the other conditions, they're not all horrible, but in some cases, they're really very far off satisfying. So it's helpful to have all of these conditions available at once. And by now choosing each of the conditions suitable for the respective target, we can run a broad scope. Note that we didn't have to try all conditions on all scope entries. We directly knew from our experience from the optimization which conditions would work on which substrate. And we can now do a broad scope of heteroarenes and also of the second half of the heteroarenes that span very broad compound properties and include a lot of bioactive moieties. With this last example of labeling, I hope that I could convince you that the central aspect of method development really leads my lab into different directions. We do traditional synthesis all the time for ligands, for catalysts, but also for its own sake to develop new synthetic methods. We have a very strong core activity at CH activation. We always look for how these can be used in, for example, medicinal chemistry programs. We always need and focus on mechanistic studies to guide new method development. And this is, for example, seen in the direct influence our mechanistic studies have had on the development of isotopic labeling techniques in my lab. With this, I'm at the end of my talk, which I cannot conclude without thanking my current lab members, which are the ones on this very recent group picture. I also thank, of course, the former group members that are listed here on the slide for contributing to the research that I've shared with you today. You've seen many of them on the slides each time when they contributed as a first or co-first author to one of the projects that I've discussed. And of course, I thank funding agencies for the support of this work and all of you for attending today's seminar. Thank you very much.
Thank you very much for your nice presentation. You showed us a lot of your directions, and we have some time for questions, dear colleagues. Somebody would like to ask something? I don't see it. Okay. Maybe everything is clear.
Yes.
Okay.
Thank you for your nice talk. And since I recently became interested in ferrocene chemistry, I'm just wondering what will happen if aryl iodide will be simply replaced by ferrocene iodide? Do we have a chance to get the same nice product with ferrocene? It's about your first slides.
Which first slide do you mean?
I guess it was 2016 work.
So it would be the carboxylic acid here, this one.
Yes.
So in principle, what the aryl iodide does here is it acts as a regular arylating agent. So what we need is, in order to introduce, for example, ferrocene, the fact that, or the requirement would be that it doesn't sidetrack. And as long as it is suitable to do the oxidative addition with the palladium-2 complex, which most aryl iodides do, and then it is suitable to do the reductive elimination, which is also known from other CH activation processes, then in principle, I would expect that this has a chance to work. But there is a few side reactions to keep in mind because the ferrocene backbone itself can be CH activated by non-directed CH activation and is, of course, known to sometimes engage as a redox active moiety. But for example, Junmin Yo in South Korea, she has developed methods that work on ferrocene. So in principle, they are compatible with related catalysts. But I cannot tell you if it works explicitly with our conditions because we haven't tried. But I don't see a fundamental reason why it shouldn't work.
Okay, thank you. And probably another question.
Okay.
It was, I guess, 22 slide number 22. Have you ever tried sulfonic acids here? Not carboxylic, but sulfonic acids. Is this possible to use this type of
sulfonic acids are not strongly coordinating enough. So What I could hope for is that a sulfonic acid would go to a ring system or so if I somehow manage to get a hydroxy group introduced, and then I can make an intramolecular sulfonyl ester. But two things would be problematic. The first is if I have the sulfonate anion, it is so stabilized that if you think about, we have phosphate anions or carbonate anions in our bases, there will just not be a strong enough interaction between the palladium catalyst and the sulfonate. So I would be trying to do an aliphatic non-directed CH activation. Or I can use, and this is something that has been done, the sulfonic acid group and use it to attach a more strongly coordinating group. But then I'm again in the stepwise process of doing a three-step protocol. And if I would get a CH activation to work, the next challenge is the reductive elimination. And as I mentioned in the context here, a reductive elimination even of the carboxylic acid is very challenging. Mm-hmm. And now again, the sulfonate is much more electron poor. So it's much harder to induce a reductive elimination. And I think in the combination, I'm quite sure that without using exogenous directing groups, this is not something that would immediately work. And I would actually rather think that this has chances with the radical hydrogen atom transfer chemistry, because there you have more oxidizing power from the radicals. You have a metal-centered radical, and this abstracts a hydrogen atom. And if you combine this with, as for example, I think the Costas group has done this, if you combine the general interaction between catalyst and substrate with ionic interactions between substrate and and ligand, then you may have a chance to get sulfonates to work.
Yes, thank you.
Okay, thank you. Dear participants, maybe other questions? So, dear Manuel, several times during your presentation, you said right ligand, right for efficient activation, right for efficient reactions and so on. Is it possible to know which ligand will be right for your reaction in prior? Or you should carry out additional experiments and only empirically obtain information about right ligand?
A little bit of both. Of course, we need to gather some evidence, but once you have this, you can often transfer it to other reactions. So since we were on this slide with the gamma lactonization, the most similar reaction that we had developed before was the fluorination. And we knew the fluorination features a challenging reductive elimination, and it features CH activation on somewhat related substrates. So it was logical to start in the same general area of chemical space and not with a completely different entity. And we knew from there that we needed to have, in order to get the desired reactivity, for example, these benzamides on the ligands. And we just quickly had to confirm that benzamides are really much better than acetamides, but we directly knew where to start. It's more difficult if you start from scratch a project. So if I would now say, let's, instead of carboxylic acids, we use amines, free amines, and other groups have done this. But I wouldn't be able to predict without the data from other groups which ligand could be good for free amides. And this is, I think, the level of predictability we have. We can go from, if we have something somewhat related, we can use this as a starting point. And this allows us to start our empirical work in the right region.
Okay. Do you use quantum chemistry or maybe popular machine learning to understand which kind of ligands do you need?
So no machine learning in the modern sense, because we would like to, if anything, arrive at rules that we can use to ourselves make predictions and where we can derive mechanistic knowledge from. So we're very much more interested in the traditional calculation of reaction mechanisms, maybe combined with linear regression analysis or so. This is something that we have tried for some of our systems. It's unpublished work, and it shows that we can understand why certain ligands change selectivities. And we have also been able to predict ligands with slightly improved selectivities, for example, by doing these computations.
Yeah, okay, nice. Thank you very much. Oh, dear colleagues, if we don't have more questions, let's thank our lecturer for very interesting presentation and nice organic chemistry, I would like to say.
Yeah, thank you very much for the invitation.
Thank you, and see you, I hope, maybe in conference in Ukraine.
I hope so.
Thanks. Have a nice evening.
You too. Goodbye.
Goodbye.